Good morning to all of you. In previous session, we have seen relationship between Fourier transform and Z transform. Right? In today's session, we will be discussing discrete Fourier transform. So here we will be looking at discrete Fourier transform, referred as DFT. Okay. So to perform the frequency analysis on discrete time signal x of n, we are simply by taking its Fourier transform, we are converting it into frequency domain, okay, or Fourier domain, right? So to perform frequency analysis on a discrete time signal x of n, okay, we convert this time domain sequence to an equivalent frequency domain representation. This representation is denoted by x of omega, which is called as what? Fourier transform. So basically what we have seen, so this x of omega is a continuous function given as n is equals to minus infinity to infinity x of n into e to the power minus j omega n, right? So this x of omega is a continuous function of frequency, and therefore it is not computationally convenient representation of the sequence x of n in the frequency domain. So this x of n can be represented by samples of its spectrum x of omega. Such frequency domain representation is called as what? Discrete Fourier transform. So instead of taking it from infinite limits, we can represent this Fourier transform over the some specific limits, right? So this discrete Fourier transform or discrete version of the Fourier transform, right, is simply denoted as x of k. Instead of taking these limits from n is equals to minus infinity to infinity, it will be taken from n is equals to 0 to n minus 1. Okay, so only capital N values of small n can be taken. Okay, and this x of n into, so when you are taking these limits from n is equals to 0 to n minus 1, this e to the power minus j omega n will be modified as e to the power minus j 2 pi k small n divided by capital N, right? So the difference between this Fourier transform and the discrete Fourier transform is simply you are replacing this omega, okay, omega by 2 pi k by capital N, right? And it has been taken for only capital N points. Okay, so here again this k, okay, this k will be having values k is equals to 0, 1, 2 and so on up to capital N minus 1, right? So therefore as these limits are from 0 to capital N minus 1, so only capital N values has been taken there, so this is also referred as N point DFT, okay, or simply it is referred as N DFT, right? So this is nothing but the N point DFT, right? So the reason of why we are simply using, or most of the time we will be using discrete Fourier transform, the only reason that this DFT will be computationally convenient compared to the Fourier transform, because Fourier transform is a continuous function of frequency, therefore it is not computationally convenient representation. Okay, so this x of n here is represented by the samples, some of the samples, not all the samples has been taken from n is equals to minus infinity to infinity, so only capital N samples has been taken, okay, from the Fourier domain, from the frequency. Okay, so only capital N samples are taken, so it is represented by some samples of the spectrum x of omega, right? So therefore this notation has been denoted as here x of k. So such frequency domain representation is called as what? Discrete Fourier transform, right? So here, as there is DFT, so we can also give the formula for the inverse discrete Fourier transform. As we know that this, as we have seen already, that x of n has the Fourier transform x of omega, right? So basically, this is reversible process. That means from x of n you can determine the Fourier transform, and from x of omega you can determine the inverse Fourier transform, right? So similarly from DFT as well you can identify the inverse DFT, right? So that means from x of k you can identify x of n, right? So this x of n has the endpoint DFT, okay, and this can be represented as, so it is written as DFT and endpoint DFT with it is represented as x of k, right? So the formula for DFT, I will just rewrite that formula here. So x of k is equals to summation n is equals to 0 to n minus 1 x of n into e to the power minus j 2 pi k n by capital N. Okay, so this is the formula for DFT. Okay, so from DFT you can identify, that is from x of k you can identify x of n. So for that purpose you have to take the inverse DFT, right? So the formula for inverse DFT is x of n is equals to 1 upon n summation k is equals to 0 to n minus 1 x of k into e to the power j 2 pi k n by capital N. Okay, and this is nothing but the formula for inverse DFT. Okay, that is IDFT. And here the k is equals to 0, 1, 2 up to n minus 1, right? And in this case this n, right, the k value summation, k variable values are from 0 to n. Similarly, the values of small n will be taken as 0, 1, 2 up to n minus 1. Okay. So these are the two formulas that you have to keep in mind. That is, first one is the DFT, that is discrete Fourier transform, and the second one is the inverse discrete Fourier transform. Okay, so in next session we'll be discussing properties of discrete Fourier transform. Okay, so we'll be discussing periodicity property and the linearity property of the discrete Fourier transform. Thank you for joining this session.